So yeah, thanks, Bill. Thanks for inviting me here. It's always fun to talk about bacteria and beaches and shellfish and stuff, for me at least. As Bill said, we'll talk about mostly some work that we've done in South Carolina to develop these forecasts, but we hope that there is good applicability for Chesapeake Bay, and we'll talk about that towards the end of the talk. We'll talk about the objectives of the current project, how well current methods to evaluate bacterial concentrations at beaches and shellfish harvest areas work, how well those tools perform, how we might be able to integrate data from additional sources to improve those tools, what those tools actually look like, how well they perform, what we're currently doing in these areas, both in South Carolina and efforts to move them farther north, and also some conclusions about the basic project that we've undertaken so far. Our first objective was to develop decision support tools for bacterial contamination at both beaches and at shellfish harvest areas in South Carolina. They both use bacteria, different bacteria, but they both use bacteria to regulate closures or issue advisories in the case of swimming beaches. So we wanted to develop some science-based decision support tools for those purposes. We also wanted to increase the utility of remote sensing data and observing system data. There are lots of data out there, and by many accounts they're kind of underutilized. We wanted to develop a concrete example of how these may be used in a project that people care about, in a product that people care about. We also wanted to illustrate a science to management application through the integration of data, and that might serve as a pilot project for a proposed Center for Integrated Information Systems at the University of South Carolina, and with other partners, including Raytheon there. When you start to look at the tools that people use for issuing beach advisories, in this case, and we'll talk about shellfish harvest areas in a moment, but when you talk about tools that people use, it's basically, it comes down to using yesterday's bacterial concentration. Because of analysis time, it takes at least 24 hours to do the analyses for the bacteria. So you've got a technician going out, say at 9 o'clock or 8 o'clock, collects a bunch of samples, and she'll bring it to the lab by, say, 1 or 2 o'clock, which is within that 6-hour window that EPA has for time from sample collection to getting it to the lab. That analysis takes 24 hours, so maybe the lab starts processing them at 2 o'clock. 24 hours later, the results are in. Takes an hour or so to read the plates. The results are transmitted to the beach program at maybe 3 o'clock the following day. So that's why I say you're lucky if you're using yesterday's bacterial data. Usually it's actually 2 days old. And then if you look at the relationship between what's happening with bacteria concentrations on day 1, which is the x-axis here, and on day 2, you can see there's just really not a real great relationship. It's not a very good and robust tool. Similarly, for shellfish harvest areas, most shellfish harvest areas in most states use rainfall to regulate closures, temporary closures of portions of shellfish harvest areas, with the assumption that with increased rainfall there will be increased loading of bacteria. Bacterial concentrations will go up, and then they'll be forced to close portions of the shellfish harvest areas based on rainfall alone. But in most cases, if you look at the relationship between 24-hour rainfall, particularly at a rain gauge, and the bacteria concentration the following day, that's also not a very good relationship. It's not a great tool to be using to regulate closures for public health purposes. So we thought we might be able to do better if we were to incorporate some of the other factors that control both loading and survival of bacteria in coastal waters. And loading, we still believe, is primarily precipitation driven, but the sources can be domestic animals, livestock, wildlife, and even fertilizer if it's not processed correctly, and sewage system components, or leaky septic systems, or sewage overflows. Once the bacteria get into the estuary or the coastal system, there are a host of other processes that can affect the survival of the bacteria. We think that solar inactivation is one of the biggest biggest ways in which bacteria are removed from the system. Solar radiation inactivates or deactivates the bacteria, essentially killing it. We have tide effects, water temperature and salinity effects, and also sedimentation. Sedimentation is also thought to be one of the largest mechanisms by which the bacteria are removed from a system. They settle out with the sediments into the system, into the sediment layer, and they were for a long time assumed to just die there. They wouldn't survive very long without outside of their host animal. But we now know that given the right conditions, they can survive and even multiply in the sediment layer. And when you have wind or wave action, those sediments can be resuspended. And as you're going out there and collecting your sample, you may encounter some bacteria that have been resuspended from the sediment layer. So all these factors can affect the bacterial concentrations that you see in a coastal system, at a beach or in an estuary where you're collecting samples for shellfish harvestarium purposes. So we thought we might be able to integrate different data sources to try and account for as many of these factors as we could. We have the same field program data set that we've had from the shellfish and the beach programs. They're very long-term and robust data sets. Remote sensing, we can get additional rainfall estimates, cloud cover, soil moisture, and wind estimates as well. And from observing systems, we can also get salinity, air temperature, solar radiation, etc. So we thought we might be able to integrate these data sources and develop some improved tools. Now, this is an example of what this might get us. This is an animation of a small storm moving across the northern coast of South Carolina. This is a boundary of one of the shellfish harvest areas, and this is the harvest area just south of it. These are watershed boundaries. And this is the rain gauge that's used to regulate these two harvest areas. So if they get rainfall at this rain gauge over an inch in 24 hours, then they will temporarily close the harvest portions of the harvest areas in these two areas. But you can see, this is the first storm I looked at to try and find this effect. The very first one. And you can see the storm goes everywhere but that rain gauge. So we thought that these remotely sensed data sources might provide a better estimate of rainfall, and then might also be a better predictor for bacterial concentrations in these estuaries and also at beaches. So our approach has been to develop two types of models, and let me step back. The hardest part historically for me, and I think of a lot of other modelers or empirical modelers, has been this part, getting all the data together in a consistent format so that it's usable. If you've got data from a lot of different sources in different formats, it's very difficult to bring it all together. At least it was for me. And recently, over the last several years, improvements in database management and scripting and programming have enabled that to really take a lot less time. And so for this project, we asked some friends of ours at the University of South Carolina to really step up and develop a very robust database for us that incorporates the remote sensing data and the observing system data in near real time. As soon as those observations are made available, they're put into the database. We can extract them very easily and develop models with them. It was a beautiful thing. Currently, we're approaching this as a kind of an ensemble approach. We're developing regression models and also classification tree models, combining those output kind of like in an ensemble output kind of like the hurricane forecasts that have one model says the hurricane's going to go one way, another says it's going to go another way. The likelihood is it's somewhere in the middle. So we're combining those output and then presenting those in a GIS delivery system. And so that's our approach for developing these models currently. So how well can we do by incorporating these additional data sources? This we're calling the mid-complexity model. This is the shellfish harvest area model example. The mid-complexity model is a bit of a misnomer. It's only three components. It's incorporating the NEXRAD data, the precipitation, salinity, and water temperature. And we primarily looked at Akika's information criterion and cross-validation results based on a random tenfold cross-validation procedure, which you can talk about or not. And in each case, this mid-complexity model using those three same parameters for each one of these harvest areas performed much better, especially in the area of cross-validation of your predicted and observed results. This is what that looks like. Your original models were the rain gauge models. This is your predicted bacterial concentration, and these are your observed bacterial concentrations in each of 4 shellfish harvest areas. This is your original model based on rain gauge precipitation, and this is this mid-complexity model that incorporates the NexRad data, the salinity data, and water temperature data. And in each case, we can see that we've been able to create a much more robust model. And these are the results of the tenfold random cross-validation. Even in the area where we don't have much variability in the bacterial concentrations, that model was suddenly significant. It was a statistically significant model, whereas this was not. There's not a whole lot of variability to predict, but we still were able to develop something that was useful. So currently, we're operating in both areas, and we're at kind of different stages at each one of these projects. The shellfish area models are not operational now, but they're probably the most robust of the models, the most well validated. And just the opposite is true for the beach applications. The beaches are completely operational for the Myrtle Beach area. They've incorporated this. This is how they're going about issuing advisories for swimmers at beaches. But they've done this with their program data, and we've helped them develop these models with their state program, field program data. We're now updating those models with these new integrated data sources, and just yesterday, the day before, I've begun to incorporate the remote sensing data and the observing system data, and it's very promising. We're really, I think, going to be able to improve those tools quite a lot. And I say we're developing this GIS delivery system. It's pretty much developed. It's just pretty much waiting on me to finish the models and hang the results on. And then it'll be updated in near real time. As soon as the results from new observations come in, we'll be able to develop predictions for the bacterial concentrations at each of 8 sections on the Myrtle Beach Grand Strand. So to kind of conclude, we, I think, pretty clearly demonstrated that we've been able to develop some improvements to decision support tools over the current methods that are in use now in South Carolina. We have increased the utility of observing system data. I think we've demonstrated that those data are very useful for this purpose. And I think we've also demonstrated that it is a good pilot project for this proposed Center for Integrated Information Systems. So having said all that, what can we do in Maryland and Virginia? Can we use that same approach to develop these kinds of predictive tools for Chesapeake Bay in Maryland, Virginia, and coastal beaches in Chesapeake Bay or in Maryland and Virginia? The field program data are nearly identical. The shellfish data especially are governed by guidelines from the Interstate Shellfish Sanitation Commission. The data that they collect are identical. The way that they process and analyze the data are nearly identical in almost all states. The remote sensing data is certainly available that we had in South Carolina. We can apply that as well here. And we also have observing system data that are available in a similar density to what we had in South Carolina. The additional thing, which I didn't think of until today, that we have in South Carolina, that we have in Maryland and Virginia that we didn't have in South Carolina are mathematical models that we can use to develop input into these statistical models too. The forecast development approach is highly transferable because it relies on this data integration, and we can develop models from these integrated data sources. So I think the approach is very transferable, and there's no reason from my perspective that we can't develop these tools for Maryland and Virginia, Chesapeake Bay, and coastal beaches as well. So with that, I'd like to acknowledge a whole bunch of folks at the South Carolina Department of Health and Environmental Control, also at the University of South Carolina and at Raytheon Corporation. And if anybody has any follow-up questions or further comments or questions about the models or where we might go, please give me a call or shoot me an email at this address. So with that, thanks very much.